April 28, 1945. East China Sea, 20 miles southeast of a Japanese convoy. At 15,000 feet, Lieutenant Commander James Patterson held the controls of his PB-4Y-2 privateer while his radar operator tracked 4 faint blips on the scope. Those dots were Japanese ships his crew would never actually lay eyes on. In the bomb bay hung 2 ASM-N-2 Bat guided missiles, technology so advanced, the Japanese Navy still couldn't comprehend what was destroying their vessels after repeated strikes. Target bearings 045, range 18 miles, the radar operator reported. These would be the only words spoken about men and ships that, for Patterson's crew, were nothing more than glowing traces on a screen. When Patterson released the missiles, they would guide themselves to their targets while his bomber turned for home, long before the enemy realized they were under attack. This was warfare transformed, not by courage or skill, but by America's ability to mass-produce autonomous weapons that removed human agency from the act of killing. The Bat represented humanity's first step into automated warfare, the ancestor of modern smart bombs and drone strikes. The ASM-N-2 Bat was the first fully autonomous guided missile used in combat. It was designed by the National Bureau of Standards under Dr. Hugh Dryden, who later became NASA's first deputy director. Unlike Germany's radio-controlled glide bombs that needed constant human guidance, the Bat was truly fire and forget, using its own radar to detect and strike targets, without further input once released. For 1945, its specifications were remarkable. Weighing 180 pounds with a 10-foot wingspan, it carried a 1,000-pound AN-M65 warhead. Its S-band radar seeker could lock onto large ships at ranges up to 20 miles in clear weather. Inside analog computing circuits, vacuum tubes and servo motors worked together to adjust control surfaces in real time, keeping the missile on course until impact. Development had begun in January 1942, when the Navy's Bureau of Ordnance recognized the need for standoff weapons, capable of hitting ships outside the reach of anti-aircraft fire. The Bureau of Standards assembled a team of aerodynamicists, Bell Labs engineers, and physicists from across the country. By March 1943, prototypes were being tested at Naval Air Station Patuxent River. What set the Bat apart wasn't only its technology, it was America's ability to build it in numbers. While Germany struggled to handcraft small batches of guided bombs, U.S. industry turned out roughly 3,000 Bats, with about 420 deployed before the war ended. The program cost $12 million around $180 million. Today, less than 0.1% of total wartime production. The Bat made its combat debut on April 23, 1945, when Squadron VPB-109 attacked Japanese shipping at Balikpapan Harbor, Borneo. Both missiles failed due to technical faults, a reminder that revolutionary weapons often came with early problems. But later missions showed their promise. On April 28, 1945, VPB-109 scored the Bat's first confirmed kill, sinking a Japanese patrol craft in Balikpapan Harbor. The missile flew roughly 9 miles from launch to impact, striking the vessel while the launching bomber was already heading home. For the Japanese crew, death came suddenly, from a silent, unseen weapon with no warning, no engine roar, and no visible attacker. The psychological shock outweighed the physical damage. Japanese sailors had been trained to expect combat through sight and sound, duels between ships, or defenses against dive bombers. The idea of a weapon that could see and think was utterly alien. By 1945, Japan had entered the war with superb torpedoes, skilled night fighting tactics, and well-trained crews. The Type 93 Long Lance torpedo was arguably the best in the world. But while Japan perfected existing tools, America created entirely new ones. The Bat integrated miniaturized radar, gyroscopic stabilization, analog computing, and automated controls, technologies Japan not only lacked, but often couldn't conceptually grasp. Captured American radar baffled Japanese engineers, who could recognize individual components but not the integrated systems. This gap extended beyond science to industry. American factories emphasized standardization and interchangeable parts. Every Bat missile was built to precise tolerances. Japanese weapons production, by contrast, remained largely artisanal, with many parts hand-fitted. The result: America could mass-produce complex guided weapons faster than Japan could turn out conventional bombs. The combat record of the Bat was modest but significant. On May 1, 1945, VPB-109 sank another small vessel, likely a patrol boat off Borneo. The squadron's logbook marked it as a confirmed strike on enemy shipping, though the vessel type wasn't clearly identified. The most notable action came on May 28, 1945, when a Bat struck the Japanese escort vessel Kaiboka Naguni near Okinawa. The ship was badly damaged and forced to limp back to port, where repairs were never completed before the war ended. On June 18, 1945, VPB-109 recorded the Bat's final confirmed kill of the war, another small patrol vessel. The squadron also managed to destroy at least one onshore oil storage tank, demonstrating that the Bat could strike fixed installations as well as moving ships. While the three confirmed sinkings, each of relatively small vessels, may appear minor compared to the thousands destroyed by conventional methods, they carried far greater symbolic weight. They proved that combat could now be carried out by machines acting without human input. Other Bat-equipped squadrons, VPB-123 and VPB-124, failed to record any verified kills. Their reports detail constant technical difficulties. Radar seekers mistaking coastlines for ships, moisture damaging delicate electronics, and difficulties identifying targets in crowded waterways. Air crews frequently jettisoned their missiles, rather than risk the danger of returning to base with armed weapons. Post-war evaluation by the Joint Army-Navy Assessment Committee judged the BAT's real-world effectiveness as mediocre. In controlled trials against isolated targets on open water, the weapon performed well. But actual combat conditions, weather interference, island clutter, and the limitations of 1940s electronics severely hampered results. Yet even these limited achievements unsettled Japanese sailors profoundly. They had no countermeasures, no comprehension of what was striking them, and no effective defense. Ships reported being struck without warning by unseen weapons that seemed to materialize from nowhere. The psychological effect outweighed the physical destruction. The Bat program highlighted the stark divide between American and Japanese approaches to warfare. The United States could invest millions into a weapon that destroyed only a few small craft, because the greater payoff lay in technological progress that would shape future wars. Japan, by contrast, could neither imagine nor develop such innovations. American industry's mass production methods also enabled swift improvements. When humidity ruined circuits, sealing techniques were upgraded. When seekers confused land with ships, design refinements improved target recognition. Each flaw discovered was quickly corrected and implemented across production. Japan's strained wartime economy could not match this responsiveness. By 1945, Japanese fleets were crippled by fuel shortages, declining ammunition quality, and failing radar sets for which spare parts were unavailable. Behind the BAT stood thousands of American scientists and engineers who treated warfare as an engineering challenge. Dr. Hugh Dryden, head of the National Bureau of Standards team, approached the project through aerodynamics and control theory, supported by specialists in emerging fields like servomechanics, analog computing, and radar. On the Japanese side, naval officers trained in traditional tactics suddenly faced weapons that made their lifetime of preparation irrelevant. Appeals to spirit, courage, and aggressive attack meant nothing against weapons that killed from beyond sight. The samurai-inspired ethos underpinning Japanese doctrine was powerless against America's industrialized science of war. For Japanese crews, the psychological strain was unique. Death in open combat was familiar and accepted, but death delivered by unseen, thinking machines challenged their understanding of honor and war itself. Survivors described feelings of helplessness and confusion, as though confronted by something unnatural. Where America sought to remove pilots from danger with technology, Japan chose the opposite course, the kamikaze. Pilots became living missiles, their sacrifice intended to offset America's technological superiority. Vice Admiral Takejiro Onishi, founder of the kamikaze program, admitted openly, "We cannot match American science, but we have what they lack, warriors willing to die." These contrasting battles, mechanical precision versus human sacrifice, captured the essence of the final Pacific struggle. Both sides inflicted terror. American sailors faced kamikaze attacks too fast to counter, while Japanese sailors endured sudden strikes from unseen guided weapons. Yet only the Bat pointed toward the future. while kamikaze symbolized the dying gasp of a warrior tradition crushed by industrial modernity. The Bat operated within America's wider campaign of technological strangulation, Operation Starvation, in which B-29 bombers scattered magnetic and acoustic mines, had by spring 1945 virtually shut down Japan's coastal shipping. U.S. submarines had destroyed most of the long-range merchant fleet. Against this backdrop, the BAT was another instrument of interdiction. Its direct toll, 3 vessels sunk, was modest, but its psychological reach amplified the effectiveness of all Allied operations. Japanese captains hesitated to sail even in regions untouched by BAT squadrons, fearing unseen attacks. American planners intentionally cultivated this fear. Intelligence units ensured Japanese awareness of the weapon, allowing captured documents to fall into enemy hands, broadcasting tales of thinking bombs and leaving survivors to spread the dread throughout the fleet. The Bat missile marked a technological milestone. Though its performance was limited by the science of the 1940s, it foreshadowed a new era. Warfare shaped not by courage or tradition, but by machines that could think and kill without human guidance. The analog computer that controlled the BAT relied on fragile vacuum tubes, prone to failure, mechanical servos that demanded exact calibration, and radar units easily disrupted by environmental conditions. To function properly, it needed near-ideal circumstances: clear skies, isolated targets, and fully operational electronics. These constraints explain its modest performance in actual combat. Out of roughly 100 missiles launched in wartime, only a small number found their mark. The Bat performed best when aimed at stationary or slow-moving ships in open waters, far from coastlines that could mislead its radar seeker. Against maneuvering vessels in crowded seas or during poor weather, it often failed completely. Even so, the weapon validated the concept of automated attack. Every guided missile that followed drew on the Bat's lessons. Engineers pinpointed what needed advancement: radar, capable of finer discrimination, sturdier electronics, and more dependable servo systems. In truth, the Bat was less a polished weapon than a technological prototype, proving that machines could carry out strikes without human direction. The final operational launch occurred on August 13, 1945, just days before Japan's surrender. A VPB Kontonova crew flying from Okinawa released 2 missiles at what they believed to be enemy ships. Both missed, an ending symbolic of the program. Disappointing in execution, yet revolutionary in implication. By the war's conclusion, around 420 Bats had been shipped to the Pacific, with only about 100 actually fired. The remainder were returned to the U.S., where testing continued until 1948. Results remained underwhelming, and by the early 1950s, the Navy had removed the BAT from service. Still, its shortcomings as a weapon masked its success as a technology demonstrator. Every subsequent American missile, from the Sidewinder to the Tomahawk, was built on the groundwork the BAT provided. Many of its engineers later shaped Cold War weapons programs. Dr. William McLean, who helped design the BAT's guidance system, went on to create the Sidewinder air-to-air missile using principles refined from the earlier project. Historians continue to debate the Bat's value. Its battlefield record, just 3 small vessels destroyed, seems hardly worth the $12 million investment and the vast engineering effort behind it. Critics argue that conventional airstrikes achieved far more destruction for far less cost, with a single torpedo attack sinking more tonnage than the entire Bat program. But this view misses the larger point. The Bat proved that guided munitions were possible, that autonomous systems could operate under combat conditions, and that the future of warfare would hinge on sensors and computing rather than human piloting skill. It marked the starting point for the precision-guided weapons that would dominate conflicts in Vietnam, the Gulf War, and beyond. The Bat also showcased the U.S. approach to innovation, the readiness to fund risky, groundbreaking technology even when immediate returns were limited. While Japan fought to preserve existing capabilities, America was already exploring entirely new classes of armaments. That mindset, more than any single weapon, helped secure victory. Japanese naval records from 1945 illustrate the confusion the Bat created. Some logs referred to steerable torpedoes, others to robot planes, and a few even speculated about death rays. Their inability to identify the weapon made any attempt at countering it impossible. Post-war interrogations of Japanese naval officers highlighted the deep psychological effect of encountering automated weapons. They had accepted being outproduced, outgunned, and outnumbered, but the idea of being killed by machines that thought on their own undermined their very assumptions about warfare. Several officers recalled that it felt less like facing superior technology and more like confronting an entirely different philosophy of war. Japan's Naval Technical Bureau tried to study the threat, but without captured examples or knowledge of the core technology, their investigations achieved nothing. Proposed countermeasures ranged from practical ideas like smoke screens to confuse radar to desperate measures such as suicide swimmers, intercepting missiles, but none were implemented before the war's end. The Bat's technological legacy is unmistakable. Its principles, fire and forget engagement, autonomous target acquisition, and long-range standoff strikes, became the foundation for modern precision weapons. Anti-ship missiles such as the Harpoon and Exocet are direct descendants, applying the same core concept with vastly improved technology. At the same time, the ethical dilemmas introduced by the BAT still resonate. It was the first weapon to kill without human direction after launch, raising timeless questions about automated violence, the absence of human judgment in lethal force, and the psychological toll of fighting unseen machine-guided enemies. These issues foreshadowed today's debates over drones and autonomous weapons. For the U.S. Navy, the Bat provided critical lessons in missile development. Its mixed performance underscored the need for reliable electronics, effective target recognition, and simplicity in operation. These insights shaped every guided missile program that followed, saving years of research and millions in resources. The program's statistics capture both its limits and its achievements. Total produced 3,000 units. Operationally deployed 420. Fired in combat 100. Confirmed sinkings 3 all small ships. Confirmed damaged 1 escort vessel Auni. Program cost $12,1945. Development time 36 months from concept to combat. By raw numbers, the Bat accomplished little, sinking just 3 vessels. But strategically, it marked a turning point. It proved that guided munitions were not only feasible but potentially decisive. The ASM-N-2 Bat stands as a watershed in military history, the first autonomous weapon to successfully kill in combat. For the Japanese sailors who faced it, the missile embodied an alien technology that nullified everything they believed about naval combat. Death arrived from an empty sky, carried by machines that could detect ships in darkness and adjust faster than any human. They became the first fighters in history to confront truly automated weapons, and their fear and confusion symbolized humanity's entry into an era where wars would be shaped as much by algorithms as by soldiers. The Bat did not win the Pacific War. That victory was secured by American production, logistics, and ultimately atomic weapons. But the Bat showed the trajectory of future conflict: precision replacing mass, automation replacing valor, and technology outmatching warrior spirit. Every smart bomb, cruise missile, and armed drone can trace its lineage back to those primitive, radar-guided bombs deployed in 1945. Today, as arguments continue over autonomous weapons and the morality of machine-driven killing, we are still grappling with the questions first raised by the Bat. If machines can choose and strike targets on their own, who bears responsibility? How do soldiers find meaning when technology negates human skill? What happens when combat becomes mathematical instead of personal? These questions, first embodied by a 1,180-pound missile with vacuum tube guidance, remain unresolved. The Bat achieved little in terms of destruction, but it opened a door that cannot be shut. It marked the dawn of automated warfare. The Japanese sailors who died without ever seeing their attacker were the earliest casualties of this new age, a reality echoed by every soldier since who has faced precision-guided weapons. They discovered in the harshest way possible that the future of war would belong not to the most courageous warriors but to the most intelligent machines. The Bat carried more than 1,000 pounds of explosives into battle. It carried the death of one era of warfare and the birth of another, an age we still inhabit, still trying to understand, and still struggling to control. In that sense, this modest, largely forgotten missile may have been the single most important weapon of World War II.